Welcome pre-calculus students to class today on this Thursday, February 6th. Hope you guys are doing well. Hope you're ready to learn some math today. If I sound like a different person, I've got the old cold thing going on, so throat and all of that kind of stuff. So hopefully you guys will be able to ignore that and still listen to the video, okay? But if my voice cracks, about 15 times during the video, just go ahead and laugh and enjoy it and then go on with the video. Let's get started right away, please. You will have a test on Monday. If you're not going to make it to my house, I would like to know that no later than Sunday, please, okay? And I hope, of course, both of you can make it. And then integrity sheets. Remember, when you walk in the door Monday, they're called integrity sheets. Integrity, because I expect you to be men of integrity. So you tell the truth, you don't lie, you take a good grade or a low grade. But remember, your integrity sheets not only give you good homework grades, they also give you 5 bonus points on your quiz if you have all of them done. So when you walk in the door on Monday, you cannot do any more of your homework for credit. Whatever you have done is what's done, so keep that in mind. Alright, here we go. Welcome to the last lesson in Chapter 10. We finally made it after 4 weeks, which is okay. We took our time, we worked hard, and I think we really learned a lot of math. We've done a lot of long videos lately with no homework until the next day. Now, by the way, that's not necessarily my favorite or non-favorite way to do it. It just depends if I feel like the whole lesson is taught better altogether as one big lump sum, or some lessons you can split up, and that's just kind of a decision I have to make. We are going to continue that trend today, a really long video, but I'm not going to give you any homework to work on. I will give you the review sheet at the end of this video, but you don't have to start working on it today if you don't want to. You are also going to see how the math we've learned previously in this chapter will be helpful with today's notes. It's all going to tie together, okay? Excuse me. Your heading today is called Probability, Lesson 10.8, and the date today, if you keep track of that, which I encourage you to do, is 02/06/14. Probability lesson 10.8. And again, I don't want your pity, but my voice is really rough, my throat is sore, so I'll be stopping a lot to drink and stuff like that. So I do apologize, but it is what it is. Okay, let's go ahead and get started. Probability lesson 10.8, February 6, 2014. It is very important that we start off today's lesson understanding that we are going to be studying 2 different types of probability. One type is called experimental, the other type is called theoretical. Okay? Experimental and theoretical probability. You need to understand that. It is important also that you understand the difference between the two. Let me grab a drink here real quick. Because if you don't understand the difference between the two, then how will you know what type of problem you're attempting to solve? The difference between these 2 types is really quite simple. Experimental probability is based on past tests ran or evidence gathered. And doesn't that make sense? An experiment is usually a test that you ran. Maybe you tested a theory that you had, or what have you. But it makes total sense to me. Theoretical probability is based on just what is about to happen without any past evidence, and obviously that is a typo. I'm going to fix that right now if I can. Theoretical probability is based on just what is about to happen without any past evidence. Examples are priceless. So I think what I need to do is give you an example, and I think when I give you an example, it'll make this pretty clear what I'm talking about, okay? So let me again read the words, and I'll give you an example. I think the example will really help. Experimental probability is based on past tests ran or evidence gathered. Theoretical probability is based on just what is about to happen without any past evidence that you've studied or looked at, okay? All right, let's continue on. You take notes here on whatever you feel like you need to, okay? Consider this situation. Matthew, we're going to use you. Yesterday, we're going to pretend that Matthew got a little bored there at his house and he flipped a coin 200 times. And he kept track. He must have been really bored, and he kept track of how many times it landed on heads. It landed on heads 112 times, and it landed on tails 88 times. What is the probability that a flipped coin will land on heads? Normally, when someone walks up to you and says, "Hey, Caleb, if I take this coin and flip it, what's the probability this coin will land on heads?" Caleb, I hope you would say 1/2, because there's two sides to the coin, and there's how many heads on the coin? One. You have 1 out of 2 chances that it's going to land on heads. In other words, we call that a 50-50 chance, right? That's why before the Super Bowl, they flipped a coin to see who would get the ball first. It's a 50-50 chance. That's theoretical probability. Let's go back a couple pages. Theoretical probability is based on just what is about to happen. You're getting ready to flip a coin, and that's what you're going to go with. However, with the given information above, remember what Matthew did, using this information here, we would say the probability of the coin landing on heads is, are you ready? 112 over 200. Because you flipped it how many total times? 200 times. And how many times did it land on heads? 112. So if you're using experimental probability, then you base your probability on the experiment that just happened, and you would say, okay, 112 times out of 200 times it landed on heads, so that's my probability. Now, yes, I would want you to reduce your fraction or type into a calculator and get out a decimal. But I hope that helps you see the difference. The type of probability you're probably used to is theoretical. Hey, what's the probability of this coin landing on heads? 1/2, But experimental probability is very, very helpful in the world of mathematics, and it's based on information given. I hope this helps explain it a little bit, okay? We're going to use your books a lot today. So go ahead and get them out now and turn to page 908. We're going to be doing a lot of word problems, and I'm not a lazy teacher, but there's just no need for me to type these problems out when they're right there in your book. There's just no need for that. So go ahead and get your books out, and please turn to page 908, and let's get started. We're going to start off today looking at experimental probability. Okay, so let's start off doing some problems dealing with experimental probability. In other words, probability based on evidence gathered or past previous tests or experiments ran. Let's take a look at page 908, example number 1. Now, as we go over these problems in your book, you're welcome to look at how the book explains them. I would just have you read the problem, then look at the screen here, not because my teaching is better than the book. In fact, I use the book a lot when I get my notes. But the reason I think it'd be wise to do that is because it might be confusing looking down at the book and looking back up and stuff like that. So I would encourage you to read the problem and just follow my notes here. Okay, example number 1. The authors of this text conducted an experimental survey to determine the number of people who are left-handed, right-handed, or both. The results are shown in the graph at the left. So if you look at the graph to the left, we have 82 people they interviewed were right-handed, 17 people were left-handed, and 1 person was ambidextrous, which means they could use both hands equally. Okay? Now, if you add all of those up, I'm going to go ahead and write this down. If you add all of those people up, we notice there was a total of 100 people that they interviewed. Okay? Interviewed 100 people. All right. Now, question A says this: what is the probability that if you close your eyes and picked one of these people out of the crowd of 100, that the person is right-handed? Okay. Well, using our statistics there, it's obvious that we would say we have actual 82 people out of 100. So there's the probability. You could say 82 over 100, or you could reduce it to 41 over 50, or you could put 8.2. All right, there we go. So that's the probability that a person is right-handed. I think that's pretty much common. It's pretty easy. 82 out of 100. Now, number 2, letter B. Determine the probability that a person is left-handed. Okay, no problem. Let's look at our table there. We're using past information gathered or tests ran. There were 17 out of 100 people who were left-handed. So the probability would be 17 over 100. That's an acceptable answer. That's fine. Or 0.17. Or you could put 82% and 17%. That's fine also. Letter C. Determine the probability that a person is ambidextrous. Okay? Well, if you look at your table, there was one person out of 100 who used both hands equally. So the probability that if you closed your eyes and walked into a room and picked one person, the probability that you would pick the person who used both hands equally would be 1 out of 100. That's an acceptable answer. That's fine. Or you could say 0.1. Excuse me, 0.01. Okay, so those are pretty cut and dried and simple. That's a good example of experimental probability. Now, letter D. This is a very good practical part of the problem. Now, look at letter D. There are 120 bowlers in most tournaments held by the Professional Bowlers Association. On the basis of the data in this experiment, how many of the bowlers would you expect to be left-handed? Okay, well, I'm going to put a B here. This was for people who use both hands well. This is for the probability that it's right-handed, and this is the probability that someone is left-handed based on the information given. Now, think about it. When I say 17 out of 100, there's really a couple different ways to do this. You are more than welcome to say, okay, 17 out of 100 are left-handed, so you could use proportion like this. Doesn't that make sense? You could say, okay, 17 over 100 are left-handed equals x out of 120. And that's a good way to do it. You would cross multiply 100 times x is 100x, 17 times 120, and then solve your equation. I don't like that method. I think there's a much easier way to do this, and I'm just going to simply, that's fine to do it that way, but I'm going to say this. Look, I know that 0.17 of means multiply. Let me say that again. Of means multiply. I know that 0.17 of the 120 bowlers are going to be left-handed. I mean, just saying probability. So of means multiply. If I take 0.17 times 120, I'm going to get 20.4. And of course, you can't have 0.4 of a person, so we're just going to say 20. The probability. That's probability. The number of bowlers that you might expect to be left-handed out of 120 would be 20. All right, because 17% or 0.17 are expected to be left-handed based on the experiment that we did. I'm not saying it's accurate, but based on the information given, that's what we come up with. All right, let me grab a drink. We'll take a look at example number 2. We're going to do about 12 examples, but remember, there's no homework. You're just going to watch the video, and then that's all you have to do today. Okay, I'm going to kind of skim through number 2 here. You can follow along. It's important for a manufacturer to maintain the quality of its products. In fact, companies hire control inspectors to make sure this happens. The goal is to produce as few defective products as possible. But since companies do produce thousands of defects, or thousands of products every day, it can't check every single product. The U.S. Department of Agriculture requires that 80% of the seeds that a company produces. Okay, something happened here. Hold on, please. Let's come out of this. All right, there we go. The U.S. Department of Agriculture requires that 80% of the seeds that a company produces must sprout. To determine the quality of the seed it produces, a company takes, now look what they do here, a company takes 500 seeds and plants them, and it finds that 417 of the seeds sprout. So they're doing an experiment. Okay, they're planting 500 seeds and 417 of the seeds sprout. They work. Now, question A says, what is the probability that a seed will sprout? Now, this is experimental probability because we're basing our information on a test that they ran. So what is the probability that a seed will sprout? Well, 417 actually sprouted out of how many? 500. So there you go. Now I really do prefer, I might even go ahead and say I mandate, I really would like your probability to be in a decimal, which is unusual for me. Usually I prefer fractions, but I would like to have your probability be in decimals. And so if you take 417 and divide it by 500, you're going to get out 8, 3, 4. So there's the probability. Now don't forget, if you wanted to write that as a percentage, as you can see in the book there, you move the decimal 2 places and you get 83.4%. All right? So there we go. So that's the probability that the seeds will sprout. Now question B says, did the seeds meet the government standard? Well, students, go up 4 lines above letter A. Do you see letter A there in your book? Letter A says, what is the probability that a seed will sprout? Go up 4 lines and you will read the U.S. Department of Agriculture requires 80% of the seeds must sprout. Well, they're doing better. They're fine. So the answer to B is yes. They met the government standards. They needed to have 80% of their seeds sprout, and they had 83.4. So they're above the standards. So yes, they definitely met the standard. Okay, let's take a look at page 909 now, example number 3. Example 3 reads as follows. There are an estimated 110,200,000 households with televisions. Each week, viewing information is collected and reported. One week, there were 12,077,000 households who watched 60 Minutes, and there were 10,672,000 households who watched the drama Lost on ABC. What is the probability that a television household tuned into 60 Minutes during the week? What is the probability that they tuned into Lost? All right. Well, I've never watched Lost. I don't know what that's all about, but I have watched 60 Minutes before. Let's go ahead and let's figure this out. First of all, let's find the probability that a television household tuned into 60 Minutes. Now, this is experimental probability because they gave you statistics, evidence gathered, from the past, and so we're basing our probability on that. So there is a total. Now come on, think this through, guys. There's the total of this many houses with televisions, 110,200,000. I think that's amazingly low. I thought there'd be a lot more than that. That's interesting. I wonder how accurate that is. But anyways, that's the total amount of households with televisions. Now, out of that total, how many people tuned into 60 Minutes? Well, it looks like to me it was 12,077,000. So, out of 110,200,000, 12,077,000 tuned into 60 Minutes. And so if you divide that out, you will get 0.110. That's your probability. If you want to convert that to a percentage, move the decimal 2 places, and you would get 11%. All right, then it says, what's the probability that a household tuned into the episode or the drama called Lost? Well, this hasn't changed. We still have this many total households in America that have a TV. And out of those total households, this many people or this many households tuned in to the drama Lost, 10,672,000. Okay, so if you type that into your calculator and divide it out, you will get 0.097. And if you want to write it as a percent, move the decimal 2 places. You could say 9.7% of the TV viewers, or the households, tuned into the drama Lost. Okay, so there was 3 good examples, actually more than 3 because each example had a couple questions, but there are some really good examples there of the TV drama, of experimental probability. All right, so there we go. Hope that's been a help to you. And now let's continue on. Let's get into theoretical probability now for a little bit, and let's take a look at some of this information here. If I seem a little distracted, sorry, there's something going on outside my window here, and I'm going to check that out. Okay, sorry about that. I am back. So let's get into theoretical probability. There are a couple of terms that we need to look at. Write these down, please. One term is called an outcome. Now, an outcome is each possible result of something occurring. And I'll give you an example of that in a second, okay? Just trust me. An outcome is each possible result of something occurring. Sample space is the set of all possible outcomes. The set of all possible outcomes. Let me give you an example, okay? Now we're dealing now with theoretical probability, so there's no past information given. What if I just said, I don't know, here's a bag of marbles, I don't know, one is red and one is green and one is blue. And I said, what's the probability of reaching into the bag and pulling out at random a red marble? Well, how many red marbles are there? One, so that's going to be your outcome, okay? And how many total marbles are there altogether? Three. Well, that's going to be your sample space. Does that help a little bit? Let me say that again. If I said you've got a bag full of marbles, you have one red, one green, and one blue or black, I forget what I said, red, green, and blue, and I said, what's the probability you'll reach into the bag and pull out a red marble? It would be 1 out of 3, because you have one marble out of 3. Well, 1 is your outcome. If there would have been 3 red marbles, and you had 5 altogether, then it would be 3 out of 5. 3 would be your outcome, and 5 would be your sample space. Okay? It's just the number up top, I guess you could say it like that, is your outcome, and the number in the bottom is your sample space. Okay? So please keep that in mind. Let's go ahead and take a look now at example number 4. I'm going to read this out loud to you. Consider the dartboard at the left. Assume that the experiment is throwing a dart and that the dart hits the board. That's a good thing. Always should hit the board. Find each of the following. Letter A, they want us to list out the outcomes. I'm going to use the word or. One outcome would be hitting the red, or another outcome could be hitting the white section. This is really pretty easy. Or another outcome could be hitting the black section. There we go. You just listed out the outcomes. The key words there were not red, white, or black. The key words were or. It's one or another, unless your dart somehow breaks in two in the midair and sticks in 2 different places. You get my point. It's going to be or, okay? Now, question B is, what is the sample space? Well, the sample space is red, white, and black. It's all 3. Because remember, the bottom of your fraction, like I showed you on the last page, the bottom of your fraction is your total number of possible outcomes. So in the bag of marbles we had 3, so the bottom of your fraction was 3. In my other example we had 5 in the bottom, there was a total of 5. You added all those up, and that's why I'm using the word and. So your possible sample space is red, white, and black, all 3 of those, okay? All 3. All right, let's move on to example number 5. Example number 5 reads as follows. A die, which is plural for dice, or excuse me, when it's more than one, you say dice. A die, that's 1 dice. A die is a cube with 6 faces, each containing a number of dots from 1 to 6. I'm sure you knew that already. Suppose a dice is rolled. Find the following. Letter A, find the outcomes. Okay, now the book doesn't use the word or like I do, but I really want you to use the word or. Your outcome could be 1, or it could be a 2, or it could be a 3, or it could be a 4, or it could be a 5, or it could be a 6. This is pretty easy stuff, okay? Those are your possible outcomes. Now your sample space, that means all of the information given there together, would be 1, 2, 3, 4, 5, and 6. Forgot my D. And 6, okay? And that's it, guys. I can't make this any simpler. That's all that you would do. They just want you to learn to list out outcomes in the sample space. That's going to be helpful later. Okay, so it's important we learn how to do that. All right, let's take a look now at example number 6 on page 911. What is the probability of rolling a 3 on a die? What is the probability of rolling a 3 on a die? Now come on, let's think about this. If I roll a die, I'm either going to get a 1 or a 2 or a 3 or a 4 or a 5 or a 6 if it's a normal standard die, and it is. What is the probability I'm going to roll a 3? Well, I have 1 chance of getting a 3, right? There's only 1 3. Now if I had a side with a 1, a 2, a 3, another side with a 3, and another side with a 3, and then a side with a 6, well, I would have 3 threes. Then I would be able to say, okay, I've got 3 chances here, or 3 opportunities to roll a 3. But that's not the case on a standard dice. I have 1 3, so I have 1 outcome, and then my total sample space altogether would be 6. So my probability of rolling a dice, or rolling a 3, excuse me, if I were to roll a die, is 1/6, 1 out of 6. Now let's take a look at number 7. What is the probability of rolling an even number on a die? Okay, this is really pretty simple stuff. And it's going to get harder, believe me. It's going to get much harder, but all right, let's see. What is the probability of rolling an even number? Well, how many even numbers do I have? Let's get my outcomes. I have 3 outcomes, and then my sample space would be all of my numbers together, 6. 3 out of 6. So you could say 1/2 is your probability, or you could put 0.5. No, I didn't put the decimal equivalent up here. I guess that would be what? 0.16 repeating. I believe I did that in my head. Either one of those two answers is fine. And then 1/2 or 0.5. Either one of those two answers is fine. I really don't want 3/6 because it could be reduced. So there we go. What's the probability of rolling an even number? 3 out of 6, 3/6, or 1/2, or 0.5. Okay? All right. Let's continue on, and let's take a look now at example number 8. Okay, hopefully you're on page 912, and hopefully by now you have figured out that you're using your pre-calculus book. If not, you're in a little bit of trouble there. The top of page 912 says we can find probabilities related to a standard deck of cards. Now personally, I'm not into playing cards, but nonetheless we can use this as an example. There's 52 playing cards. I'm glad they drew a picture for you, because I'm not familiar at all with playing cards. I don't even know half the stuff that's here, so I'm glad they've given us a good picture so we can use this. And such a deck is made up as shown in the following figure. So there's a picture of all the cards in a regular standard deck of playing cards. Question 8. What is the probability of drawing an ace card from a well-shuffled deck of cards? Okay, well, here we go. If you'll look to the far left, we have, you see when you look at the cards, the diagram, the picture, if you'll look to the far left, going down, you'll see an A, an A, an A, and an A. One is a spades, one is a clubs, one is a heart, and one is a diamond. Okay? And so there's how many ace cards? In other words, how many ace cards, or how many outcomes do I have in that whole deck of cards? Well, there's 4. There's 4 possible ace cards I could pull out. Now, how many total cards are there altogether? Well, if you will look up at the paragraph at the very top of the page, it tells you there's 52 cards in a standard deck of playing cards. So there we go. This is just not that difficult. The probability is 4 out of 52. If you were to reduce that, you would get 1/13. All right, don't have the decimal. I don't have the decimal equivalency, but you could type that in and get that on your own. But this is an acceptable answer, 1/13. All right, let's take a look now at number 9. Suppose that we select, without looking, 1 marble from a bag, and in this marble we have 3. In this bag we have 3 red marbles and 4 greens. So 3 red and 4 green. There we go. What is the probability that I will pull out a red marble? Well, my outcomes are 3 because I have 3 red marbles. My total sample space is 7. So the probability is 3 out of 7, or 3/7. The probability that I will reach into the bag and pull out a red marble is 3/7. By the way, whenever you hear the word odds is a little different. This is just kind of free right here. You don't need to know this for a test or a quiz, but if I asked you to tell me the odds of getting a marble out of that bag, a red marble, the odds would be 3/4, or 3-4. And that's the comparison of the red to the green marble. So odds, finding the odds of something is not the same thing as finding the probability. Okay, they are 2 different things, just so you know that. Okay, so the probability of blindly reaching into a bag and pulling out a red marble is 3/7. 3/7. Okay, now I want to pause for a second. I did not forget to type this. I just wanted to get to it when we got to it. Let me stick an extra page in here. If you'll look at the bottom of page 912, they give you a probability, so 3 probability properties. I'm not going to test you on this, but I want you to be familiar with this. Okay, probability always ranges write this down in your notes please, it's less than or equal to 1 or it's greater than or equal to 0. Now, if I tell you the probability of something is 1, that means it will happen. For example, if I said to you, what's the probability of my flipping a coin and it will land on heads or tails, either one? Well, obviously, it's going to happen. I mean, the coin's going to land on heads or tails. So when the outcome is for sure going to happen, the probability is 1. Now, what if I said to you, what's the probability of me flipping this coin and it lands on the side with a soccer ball on it? Well, that probability would be 0 because we'll say we're using a quarter. A quarter doesn't have a soccer ball on it. So what's the probability of flipping a quarter and it lands on the side with a soccer ball? 0. It's not going to happen. So whenever a probability is 0, that means the situation will not happen for sure. And whenever probability is 1, the answer is 1, that means that the situation will happen for sure. I could say this, what's the probability of me walking into the mall and blindly closing my eyes and picking out a person? What's the probability that I would pick out a male or a female? Well, the probability is 1 because I'm going to get a male or a female if I pick a person. And then, of course, anything in between there is the probability we've been dealing with before. And there'll be you will never get probability out that's going to be a negative number, and you will never get probability that's going to be like 1.6. Probability will always fall between 0 and 1. Okay? All right, wanted to throw that out there to you real quick. And now let's continue on to example number 10. Now we are getting into the world of pretty difficult probability. So buckle your seatbelt and say a prayer, and let's go ahead and get started. By the way, we just have 3 problems left to give you some daylight here, 10, 11, and 12. So hang in there. All right. Now, if you'll listen carefully, I'm not bragging, but I can explain this well, but you're going to have to listen. Page 913, example 10. Suppose that 2 cards are drawn from a well-shuffled deck of 52 cards. What is the probability that both of them are spades? Now, if you'll listen to me, I can help you. First of all, take your eyes and look over at page 912. Okay? You'll see the picture there of all the playing cards listed out. Now, when I say rows, look up here at the screen, please. Rows are things that go across like this. So if I said look at row number 3, I mean these cards right here. Columns go up and down. So if I said to look at row 3, column 5, you would go, or if I just said look at column 5, this is column 5 right here going down. Rows go across, columns go up and down. Having said that, I would like you to look at rows 1 and 2, please. Both of those are black cards. I am not a playing card person. I can honestly tell you I don't know which one of those is clubs and which one of those is spades. Now, I know the red cards, the bottom 2 rows, you can obviously tell one's a heart and one's a diamond. That's easy. I know hearts and diamonds. So I don't know which one of those 2 rows are spades and which one's clubs, but we're just going to pretend the top row is spades. It really doesn't matter, guys, because both of those top rows have the same amount of cards, okay? But either way, what they're asking you is this: what is the probability that you will pull out 2 cards that are they both have to be spades, okay? Well, if you'll think about it, now I'll do the best I can to explain this, but it really makes sense if you'll just listen to me. First of all, if I pulled out a king spades and a 6 of spades, or if I pulled out a 6 of spades or a king of spades, either one, that is going to be the same group, guys. That's the exact same group. So order doesn't matter. Order does not matter. So if order doesn't matter, I'm dealing with combinations. We learned that about, I don't know, 2, 3, 4 school days ago. I'm dealing with combinations. So my possible outcomes, now see if this makes sense. My possible outcomes are this. I want to know out of 13 cards, how many sets of 2 I can get out of that, or subsets of 2. Why 13, Mr. Earhart? Well, if you go to the top row and count across, you'll see there are 13 black cards going across. Now, I didn't say 2 rows, just the top 1 row, count across, you'll see there are 13 cards. And I want to pull out of those 13 sets of 2. So if I find out how many that would be, that gives me my total possible outcomes. Now you say, oh, I know the sample space, Mr. Earhart. The sample space is 52 because there's 52 cards. Now hold on, that's not true. You're pulling out 2 cards. Okay, before we were pulling out one card, and we knew there were 52 one cards in the deck, or 52 cards, so the denominator is 52. In this case, we're pulling out sets of 2 out of how many cards? Well, there's 52 cards, and we're pulling out sets of 2. Okay, and so that's how you would set this up. Now, we have learned in the past how to solve this. Okay, let's start with your numerator. Your new member 13C2 would be, remember how we do this? Just like this, all over 2 factorial. And then in the denominator 52C2 would be 52, and then a P, and then a 2, all over 2 factorial. Now, that's a lot of calculator work, and I believe in being a helpful teacher, but there's no need to go over all of this again. You've had this on quizzes and tests, and, well, quizzes and homework and all that stuff. If you type this correctly into your calculator, you would get 78 for your numerator. You can see that right there in the book. And in your denominator, you get 1,326. Now, Mr. Earhart, would you really make us reduce that in a test or a quiz? Yes, I would, because your calculator does it for you. You just type it in your ABC button for you, Caleb, or Matthew, your division button, 78 divided by 1326, then hit math, enter, enter, and this fraction would pop up on your screen, 1/17. This is a tough problem. You might have to rewind the video and watch this explanation again, but as you watch it over and over, probably about 50 times, I'm kidding, but it'll take a while for this to sink in, but it really does make sense. The possible outcomes was taking a total set of 13 cards and taking those 13 cards in sets of 2. The total sample space was 52 cards, taking them out in sets of 2, and this would be your answer. All right, let's take a look at 2 more problems, next number 11 and then number 12. Example number 11 now is definitely difficult, so please pay attention. I will do the best I can to explain this to you. Suppose that 3 people are selected at random from a group that consists of 6 women, 6 men, and 4 women. Let me read that again. You're selecting 3 people at random from a group of 10 people, and out of that 10 people, there's 6 men and 4 women. What is the probability that 1 man and 2 women are selected? All right, what is the probability? Well, let's think this through. We have to first of all start with my outcomes. Okay. Out of the men, we want 1 to be picked. Okay, let's write this down. Okay, we have 6 men, 2, 3, 4, 5, 6, 4 women, 1, 2, 3, 4, and we're going to select a group of 3, and the group of 3 has to have 1 man and 2 women. This is what we're going to select right here. That's the group we want. Okay, well, first of all, let's find our possible outcomes, okay? What are our possible outcomes? Well, that's a really good division line. Let's try that again. There we go. Well, first of all, I have to find out how many sets of 2 I could take from the men, okay? Or excuse me, I'm sorry, 1, because look at our selection, we're pulling out 1 man, okay? So I have to figure out how many sets of 1 I can pull out of this, all right? So that means I'm taking combinations out of 6 in groups of 1 times, now for the women, I'm pulling out 2 women. So I have 4 women, and I want to know how many sets of 2 I can pull out. Now I'm using combinations because order doesn't matter. If I pull out Mary and Susie, that's the exact same group as Susie and Mary. So order does not matter, and when order does not matter, you use combinations. Now let's think about our total sample space. Our total sample space is how many people? 10, and we're pulling out how many people out of that sample space? We're pulling out 3. Okay, so that means I have a set of 10 people, and I'm pulling out sets of 3 out of that 10. And there you go. That's it. Now I'm going to try to erase some of this stuff to get some more room. And here we go. Let's go ahead and get started here. I'm going to slide this up here, but you know we're dealing with, problem number, example number 11. All right, here we go. Now let's get some work going on here. First of all, let's deal with the numerator. The numerator up top, I would have the same thing as 6p1 over 1 factorial times over 2 factorial. And then down here I would have 10p3 over 3 factorial. Now obviously this one here is just going to be 6. I mean, think about it. You're taking one blank out of 6, you put your blank and put a 6 in it, and 1 factorial is 1, so 6 over 1. I'm not going to figure all these out for you. Again, guys, we've done so many of these. Please don't think I'm being lazy, but we have done so many of these. You end up with 3 up top and 10 in the denominator. You can work that out on your own. I'm not being lazy. That we can figure this out, and maybe I will hedge a little bit. This would be 6, and this here would be, remember you have 4 total, taking it permutations of 2, so it'd be 4 times 3 is 12, divided by 2 times 1. I'm also getting 6. Now I'm doing it in my head, so if I make a mistake, please be patient with me. But I'm getting a 6 right here. So 6 times 6 would be 36 for your numerator. Your denominator would be 10 taken in taken in groups of 3, 10 permutations of 3. So 10 times 9 times 8. All over 3 times 2. 2 becomes a 1. This becomes a 4. 3 becomes a 1. This becomes a 3. 120. I think that's 120. And if you divide by 12, you would get 3/10. So yes, there we go. So I kind of worked that out for you quickly just to be nice, but we know how to do this. We've done tons of them. The main problem you're going to have is setting these things up. And I'm telling you, you might want to rewind this problem and watch it again. But this is how you figure these out, okay? All right, let's take a look at one more example, and we're finally finished. Example number 12. Now, when we look at number 12, I would like to pause and say this. It's really difficult to do number 10, if you'll look back at number 10, unless you had the cards drawn out for you over on page 912. All the playing cards listed out. That's such a help, okay? It really is. And so that's what they've done on number 12. I mean, Mr. Earhart, isn't there a mathematical way to do it without drawing out all of this rolling of the dice? It is, but you have to be able to see how many different outcomes, outcomes and sample spaces you have, just like the cards. So it's not that it can't be done mathematically. We just have to see all of our options so we can then do it mathematically, okay? So question 12 says, what is the probability of getting a total of 8 on a roll of a pair of dice? So if you've noticed, they've listed out all the different dice. Now they use the red and the blue dice, so you can see that they're just see a little easier the different outcomes or the sample space. You could get a 1 and a 6. The 1 being on the red dice and the 6 being on the blue dice, or go all the way down to the bottom right corner. You could get a 6 on the red dice and a 1 on the blue dice, okay? So all of those are definitely possibilities. And so when we roll the dice, all of these different options come up. But if you'll look, they took a highlighter and they highlighted the ones that add up to 8. 2 and 6, 3 and 5, 4 and 4, 5 and 3, 6 and 2. Okay? And so with that in mind, now, order does matter on this one, okay? Because a 2 and a 6 with the red and the blue dice is not the same thing as a 6 and a 2. 6 with the red and 2 with the blue. There is a difference there. Well, Mr. Earhart, you said there was no difference when it came to the black spades. That's because they were all spades. So it didn't matter if you pulled out a 2 first and then a 3, or a 3 first and a 2. They were both spades. So that was the exact same group. That didn't matter here. Rolling a 2 on one dice and a 6 on another is not the same as rolling 6 on another and a 2 on the other dice. Okay, it is, I'm probably being a little confusing, but there is a difference there, okay, because you have 2 different dice that you're using and a different number can come up on each one. So what is the probability of getting a total of 8 on a roll of dice? Well, students, your outcomes would obviously be 8 because excuse me, that's not correct. Your outcome would obviously be 5 because there are 5 possible sets of different ways of rolling an 8. And they've highlighted that for you: a 2, 6, a 3, 5, a 4, and a 4, a 5, and a 3, and a 6, and a 2. So that's the amount of possible outcomes you have. Your sample space, if you add up all of those possible rolls, is 36. That's your sample space. So that's the probability, 5 out of 36. Now you could type that in your calculator and get a decimal if you want to, but that's how you would do that one, okay? So I know this stuff can be a little confusing, and I feel your pain, but it's part of math, and the best solution to, let me make up a word here, to unconfusing yourself is practice. Practice, practice, practice. Okay, I'm going to end this video. I've talked long enough. Here's your review sheet. You do not have to get to work on it. I would like to point out to you there's 35 problems. If you walk in my door Monday with this many of them done, that is your business, but I'm not going to feel bad for you. Your test is still going to be due on Wednesday. I mean, if you broke this up into just 10 problems a day, do 10 on Friday, 10 on Saturday, and 10 on Sunday, hey, you've only got 5 left to do. And plus, you would have a really organized list of which problems you knew how to do and which ones you didn't know how to do. You can check all the odds in the back of the book, and the even ones you can listen to my video, which I will post sometime tomorrow, maybe Saturday. Tomorrow, Saturday, I'll post the video with all these worked out, and you can use that, okay? So, anyways, I hope you guys have a good day. I hope this video has not been too confusing. Congratulations on finishing Chapter 10, and we will see you on Monday for a test, and I will have the review sheet up and running for you tomorrow or Saturday.